How did American artillery find targets in the winter of 1944 across the dense Ardennes? Shells detonated directly over trenches without touching the surface. Down in a foxhole, a soldier heard the distant rumble of a 155mm howitzer battery miles away. There was no whistling descent or deep thud of metal striking the frozen earth. A silent arrival ended in an explosion perfectly above the canopy. The physical geometry of the airburst dictated a strict downward vector, sending steel fragments straight into the dugout. Standard 42-kilogram high-explosive projectiles delivered a lethal fragmentation radius of 50 meters upon aerial detonation. A classic trench offered zero protection against shrapnel arriving vertically from the sky. Every volley blanketed platoons under a cone of steel, bypassing natural terrain barriers completely. These mid-air detonations erased the mechanical advantage of subterranean cover. Prisoners from the Ardennes offensive confirmed the failure of standard defensive tactics against these munitions. Surviving below ground level became a geometric impossibility under this downward fragmentation. German units actively rejected commands to hold their positions during sustained barrages. Infantry formations abandoned their trenches and charged directly at American lines to surrender. The time shell promised perfect accuracy. Reality was different. Lethality depended on air density and barrel wear. The Ardennes strikes broke established rules. Past artillery used two mechanical detonation methods. Both carried fatal flaws. Before 1944, infantry learned a simple tactic. They dug deep trenches. Soldiers waited below the surface. They simply outlasted the bombardment. The contact fuse required physical impact. It needed solid concrete or rock. The shell flew its arc. The metal nose fairing struck down. Impact crushed the firing pin. The primer ignited. Soft spring mud changed the outcome. The contact shell hit the wet earth. A dull thud. The heavy projectile buried itself deep. Soft ground absorbed the explosive blast. Shrapnel flew upward and outward. The trench below remained completely untouched. Troops inside survived. The time fuse offered new hope. Gunners set a clockwork mechanism. The shell detonated high in the void. It exploded directly above the target. Theory was simple. Reality proved much harder. Calculations required exact precision, but artillery metal fatigues over time. The standard 105mm howitzer degrades. Constant firing wears down the barrel rifling. Muzzle velocity drops with every shot. The steel shell flies slightly slower. Predicting exact flight time became impossible. Timers fired early in empty sky, or they detonated late in the dirt. Accuracy demanded the exact target range. It demanded the precise shell weight. Gunners carefully weighed the propellant charges. Shell weight varied straight from the factory. Even fresh paint added extra grams. Powder batches burned at different speeds. Every single detail mattered. Variables stacked up. Local weather conditions altered the steep trajectory. Changing air density shifted the flight path. High humidity slowed the spinning steel down. Cold temperatures altered the powder burn rate. Calculations needed perfect data across the board. Changing any one of the 5 flight variables instantly ruined the entire ballistic calculation for the front-line artillerymen. How do fleet gunners shoot down a target changing altitude every single second? The Navy demanded that physicists engineer a shell equipped with its own internal radar. This time fuse problem reached a critical threshold during the summer of 1940, coinciding with the Battle of Britain. Physicist Merle Tuve received a specific Navy assignment at the Carnegie Institution. He joined the newly formed National Defense Research Committee to mobilize American science for an approaching war. The core problem involved closing speeds. A Junkers Ju-87 dive bomber plummeted toward ships at 600 kilometers per hour, leaving anti-aircraft crews mere seconds to input data. A shell missing by 20 feet remained exactly as useless as one missing by 200. Autonomy became the only practical answer to these increasing aircraft speeds. The munition required sensors to detect the target and detonate independently. The Tizard mission transferred preliminary British research data directly to the Americans in September 1940. Why did German engineers fail to reverse engineer unexploded munitions? They predetermined that glass could never survive a gunshot. The 1940 secret held even after General George Patton deployed the weapons en masse. Patton informed the War Department that these fuses won the Battle of the Bulge. Censors placed the American press under a strict gag order. Reporters could not mention the operating principle until the war ended. German specialists analyzed captured fragments. They found glass vacuum tubes. These fragile parts belonged in stationary receivers, not in flying metal. Their doctrines blinded them. German science officially recognized the creation of a radio fuse as a physically unfeasible task. How did two salvos from the USS Helena alter anti-aircraft artillery? The newly developed shells no longer required a direct hit. On January 5, 1943, the cruiser tracked incoming Japanese dive bombers near Guadalcanal. The ship deployed 15 127mm guns to project a dense defensive curtain across the sky. Gunners fired 2 brief salvos toward the retreating aircraft. Japanese pilots pulled away to evade a direct strike, but the projectiles detonated nearby. A sudden mid-air explosion tore through the enemy formation as the internal radio fuse sensed the exact proximity and triggered the explosive charge. This technology transformed a clear trajectory miss into guaranteed target destruction. It marked the first combat kill by a radio-fused weapon in history. The crew of the cruiser never fully realized what they just did. 20,000 times the force of gravity. That is the physical pressure inside a naval gun. The cruiser shell hit its mark only because physicists from Section T solved a critical problem. They protected fragile glass radio tubes from the violence of an artillery launch. At the moment of firing, the shell accelerates instantly. Standard 5-inch projectiles weighed 24 kilograms. The steel rifling inside the barrel grips the heavy casing. It spins the unit at 25,000 revolutions per minute. Ordinary 1940s household radio tubes shattered just falling off a desk. Section T engineers had to make them survive inside a cannon. Germany declared this physical challenge impossible. The American team engineered a mechanical armor. They packed the miniaturized glass vacuum tubes into a dense suspension of wax and oil. This thick liquid mixture absorbed the massive shock. It equalized the extreme physical stress across the fragile glass components during the launch. The tubes did not break. They held together inside the heavy steel shell. Then came the electrical sequence. A built-in safety delay prevented the battery from activating the circuit immediately upon firing. It waited several milliseconds. This brief pause gave the shell enough time to safely clear the deck of the gun crew. Once armed, the fuse broadcast a continuous radio signal toward the target. The returning frequency triggered the detonation at lethal range. By late 1942, the Navy possessed a fully operational weapon. How much did producing 22 million secret fuses cost? $1 billion. Industrial giants like RCA and Eastman Kodak delivered 40,000 fully assembled units every single day. The successful operation of glass tubes launched these manufacturing processes across over 100 separate facilities. Considering the total United States defense budget hovered around $80 billion, this specific project became a massive single investment. Female assembly workers constructed these delicate components by hand under strict security protocols. Guards searched them at factory entrances daily, and management never revealed the true nature of their labor. The scale of constant volume production altered the underlying economic mathematics of the supply chain. A single unit, originally priced at $732 in 1942, plummeted to exactly $18 by 1945. The most advanced weapon multiplied endlessly. Factories produced millions. European artillery faced a strict ban. They fired nothing. 40,000 secret fuses left assembly lines daily. None reached the front. Command denied every request. Fear dictated this policy. Reverse engineering was the primary threat. Section T evaluated German manufacturing capability. The enemy possessed vast factory networks. They lacked one breakthrough. They could not miniaturize components. One captured unit meant disaster. The advantage would disappear overnight. A 3% dud rate was standard. Some shells failed. They hit dirt. They never detonated. Intact electronics survived in the cold mud. German patrols would find them. Engineers would open the casing. They would copy them. Strict directives controlled the deployment. 1943 established rigid rules. 1944 maintained the embargo. Navy ships deployed fuses freely. Failed shells sank fast. Anti-aircraft batteries also received full approval because their unexploded stray rounds fell safely behind friendly territorial lines. On the Western Front, command banned them completely. What forced General Eisenhower to break the embargo? The V-1 cruise missiles over London. By mid-1944, Eisenhower petitioned the combined chiefs of staff for a special exception. They approved. British anti-aircraft batteries on the coast opened fire. Radar-guided shells detonated directly in the path of the flying bombs. A V-1 cruised at 640 kilometers per hour. Standard mechanical timers rarely hit them. The new fuses changed the math. The mechanical hum of the pulse jet engine echoed below the clouds. A sudden mid-air explosion severed the noise. Before radar fuses, standard fire intercepted just 17% of targets. By late summer, the coastal gun belt destroyed 74% of all incoming drones. On exceptional days, the kill rate hit 82%. Prime Minister Winston Churchill publicly praised the American technology. He stated the fuses proved highly potent against the unmanned aircraft. But millions of ready shells sat fully assembled in European hangars. They waited in crates, locked away until the restriction lifted. Churchill expressed public gratitude for the shipments, while millions of artillery rounds rested in European warehouses under a rigid ban. How do 155mm shells reach deep trenches? They detonate between 9 and 15 meters above the ground. The heavy projectile arcs toward the frozen front line. An internal transmitter broadcasts continuous radio waves. Radio signals travel at 300,000 kilometers per second. They shoot forward. They reflect off the hard frozen earth below. The miniature fuse reads this radar bounce instantly. At exactly 9 meters altitude, the internal circuit closes. The steel shell explodes. A downward cone of jagged steel sweeps the terrain. Trenches offer nothing. Standard contact fuses hit soft Ardennes snow. The snowy impact absorbs the lethal shockwave. They bury their blast energy deep underground. The proximity fuse radically changes this physical geometry. It triggers a massive airborne fragmentation strike. German commanders counted on heavy winter weather. Thick cloud cover grounded Allied support planes. Forward artillery observers saw nothing through the fog, but radar fuses ignore the clouds. Radio waves need no human visual spotters. The mechanism corrects its detonation timing automatically. Weather becomes irrelevant. General Patton tested this new lethal math. A German battalion pushed toward the American lines. They attempted crossing the river near Echternach. It was Christmas. American artillery batteries fired proximity-fused explosive rounds. The night sky erupted over the river crossing. 702 German soldiers died there. Shattered bodies lined the frozen riverbanks. A single barrage erased the entire German assault unit. Patton wrote directly to the War Department. He analyzed it. General Patton recorded that when all armies acquire this weapon, commanders will have to devise entirely new methods of warfare. Colonel George Axelson commanded the 406th Artillery Group while sitting on a stockpile of embargoed 155mm shells. On December 16, 1944, the German armor punched through a 130-kilometer front. American cavalry units called for fire support to hold the lines. Command had shipped the proximity-fused ammunition to the European theater, but headquarters withheld the deployment authorization. Axelson made a decision to ignore the strategic restriction. He ordered his gunners to unseal the crates and fire the restricted shells. The local emergency overrode the standing orders. 2 days later, General Eisenhower assessed the situation across the theater. He formally requested the combined chiefs of staff to lift the embargo. Why did German engineers fail to copy this technology? The internal self-destruct mechanism incinerated every unexploded shell. Captured troops detailed the incoming fire during interrogations. They imagined impossibly precise mechanical timers, a perfect clockwork. Nobody suspected radar. The primary radar sequence failed. A backup circuit activated immediately. The fuse triggered a dedicated internal explosive. Vacuum tubes shattered. Copper burned away. Internal electronics melted completely before ground impact. Search teams scoured the craters. They found only scorched metal fragments. Teams found nothing. The core secret remained invisible. Prisoners remembered the specific terrifying noise. Frequent mid-air bursts cracking directly overhead. Heavy shrapnel rained down vertically. Deep trenches offered zero protection. The strict classification held tight until VE Day. American press faced complete domestic censorship. The enemy never captured one functional unit. Nazi Germany never fielded an equivalent weapon. Standard anti-aircraft batteries struggled against bombers. Gunners previously fired thousands of rounds per target. The radio fuse changed the combat math. American factories produced 22 million units. These devices fit inside standard artillery shells. Winston Churchill praised the invention. It saved London. Vannevar Bush directed the scientific war effort. He analyzed the massive field data. After reviewing the dramatically reduced ammunition expenditure across the entire European theater, he concluded that the proximity fuse multiplied anti-aircraft efficiency by exactly 7. In 1942, engineers forced glass vacuum tubes to withstand the violent acceleration of an artillery launch, while today, this exact principle guides modern air defense networks. Merle Tuva and his team at Section T engineered a mechanical structure to protect these internal components from immediate destruction. 20,000 Gs. That physical overload slammed into the glass bulbs the exact moment the weapon fired. Because those tubes survived the initial shock, contemporary surface-to-air systems like the Patriot missile still rely on radar fuses derived directly from those wartime tests. The technical lineage remains unbroken. A single 155mm shell detonating over a snow-covered field in the Ardennes.